Okay, so we go to the next thermodynamic properties of the matters. This is interesting. When you discuss about thermodynamics, it's not only about energy balance, mass balance, or entropy balance, but also we call it thermodynamic properties, or somehow you say thermophysical properties. What this one actually? This is actually discuss about the properties of the matter. For example, if I have ethanol and then I have or another organic solvent like MIBK, methyl isobutyl ketone, or acetone is the most easy example, acetone and ethanol. So they have different properties. Properties, it means like different specifications of the or character of the fluids. For example, I can give you easily example like boiling point. Boiling point is one of the properties. So boiling point of acetone is different with the ethanol, right? I believe that you know ethanol is 78 degrees C and for the acetone is 55 degrees C. So they are totally different. The same like characteristic of the fluids. So same like here, we have the pressure, we have the volume, the temperature, internal energy, you have enthalpy, you have entropy, free Helmholtz free energy, you have the for the Gibbs energy, this is not M, but this is mu. So we have the chemical potential, we have fugacity, we have the constant volume, we have the constant pressure, and so on. This is all its thermodynamic properties. And everything, it relates about the state of change. State change. So the thermodynamic mostly discuss about if I have state 1, this is state 2. So I have the state 1. State 1, for example, we always discuss T1, P1, yeah, V1. In here the same, I have T2, P2, V2. So this is, it's all is about the conditions. So the thermodynamic properties change is about how the state 1 go to the state 2. When I have the temperature 25, I heat my system to the 55 with the same pressure. They always discuss about the state change. Condition is different between initial and the final. This is, we call it state change. And of course, the thermodynamic property will change. For example, the internal energy. That's why we have delta U, delta H, yeah, delta S. This is all is discussed about property changes. So how to specify the systems that the degree about how we define if we have supposed to be system and we want to measure the conditions itself, we can calculate or we can take a look for the degree of freedom. So what is this degree of freedom? It indicates about the which kind of the constraint that you can fix. For example, I have here the state of change and the degree of freedoms from the phase rule. I believe you ever use this. This is F is degree of freedom equal to the 2 plus the compound. This is component or compound minus the phase. For example, I have water. Water, of course, the compound is only 1. And then the phase of water is a liquid phase. So you have only one phase. So you can calculate here F equal to the C minus P plus 2. I have 1 minus 1 plus 2. So your degree of freedom is 2. It means that you can define the temperature, pressure, temperature, volume, pressure, volume in your system. So you can fix these ones. So if supposed to be I have a water, I want to boil the water at the pressure maybe 180 m. So you can fix like 100 degrees C and the pressure is 180 m. So later on, you can get the internal energy, enthalpy, or any kinds of the properties. Another example, the degree of freedom, you have two the same, yeah, single phase, and here single component. So if I have, like, for example, single component, the two phase in here, I have vapor and liquid. So I have F equal to the one component minus 2 plus 2. So it means that I only have 1 degree of freedom. Means that I only can define the temperature only. I can control my system only temperature or only pressures. So then you will get the the properties of change. The other thermodynamic properties for the single system and single component, we can write the function of the temperature and the pressure, or function the temperature and then the volume. So T and P are easier to measure, yeah, and manipulate than others. For example, the temperature and the pressure, like we discussed in chapter 1. Temperature, we can use the temperature indicator. Pressure also the same, pressure indicator. It's easy to measure, like for the T and P. I can use the thermocouple or I can use the pressure indicator. Then I will get the temperature and then I will get the pressure. So how about the volume? Volume is not easy to control, yeah. The T and P is easy to control. So for example, in here we have the volumetric EOS. It means equations of state. This is somehow we write EOS, equation of state. So we can use PVT or the thermal EOS, equations of state. So EOS for the thermal, it means that we need to control internal energy, the temperature, and then the volume. But to measure the UV is not easy. So that's why in the company, even the application, we mostly use the P, V, and T, and then calculates other thermodynamic properties. One example in here, we have ideal gas. Yeah, ideal gas. In the real, if you ask me, like, we have ideal gas. So the ideal gas is mostly happen if you have the cengkong chi, yeah? It was the vacuum pump. So the cengkong for the vacuum pump, because the vacuum pump, we don't have the interaction between the gas each other. So you can assume that the system, it tends to be the ideal gas. No interaction because the pressure is very low. It's like almost under zero, yeah? Maybe minus 0.2 or 0.00 something, like 0.2 or 0.7, yeah, around this is minus. And then we can use the ideal gas law equation of states, like PV equal to the RT. So in here, the volumes, they have the property of underline because the volume is based on the size. It's if you still remember about intensive property and extensive properties. So the volume is extensive property, but the P and T is the intensive property. So extensive property, it's depend on the size. That's why here we have the V underline. So U underline is function of the temperature, yeah? Because to calculate the U, you can define the temperature and then for the ideal gas, yeah? And then the H or enthalpy, you can solve with the function of the temperature of the ideal gas. How about the real fluids? Real fluids, the T will change with the pressure, or we can use the in the case of the degree of freedom 2, we can depend on the TV or T and P. They will change for the real fluids. So I believe, like, you know what's the difference between ideal fluids and then the real fluids. So real fluids, they have interaction each other between the A and then component B, B to the C. So this is for the real fluids. Okay, then we go to the others. This is unique properties that we will discuss on the thermodynamics. We call it, this one is the temperature dependence, U and V. This is, we call it the properties of matters. Like, if you take a look for this case, we have the the temperature dependence of the internal energy and the enthalpy for the all substance. This is not only in the ideal gas, can be found by measuring like the temperature rise that accompanies of the heat flow. Like if you supposed to be have the heat flow and then you increase the temperature, so this is will change into the closed stationary system. So if the sufficiently the small quantity of the heat is add into the system, if we add the heat into the system just a little bit, and they have the inversely proportional to the number of mole in the system. So we can write that Q divided by N equal to the C delta T. So this is, we call it the, if we add into to the small heat into the system. So what's the C? C, it's, we call it parameter. They are function of the temperature, and the Q is the heat added to the system between T1 and T2, between the time. So we can simplify, write C is equal to the temperature at T2 minus temperature at T1. Then we can try to expand. If the object of this experiment is accurately to measure what kind of the parameter, because we have the parameter Cp and Cv. One is constant volume, the other is constant pressure. So we can start to define this parameter. So measurement is made at the constant V and the Ws equal to B0. So I just write directly because if you want to expand, you can start with the energy balance. But here we can start directly like U, it's at the T2 minus U, it's equal to T1. So we can use the Q equal to the, because here Q is divided by N C delta T. So you can equal to the N because it's constant V. So we can CV and T at T2 minus T at T1. So here we can rewrite for the CV, it's become CV equal to T1. So we can simplify, divide CV equal to the U T2 minus U T1 divided N T2 minus T1. So from where this one? From energy balance. If you supposed to be have the constant V, Ws equal to B0, you have constant volume. Automatically your Wf equal to B0, yeah? Minus P dV divided dt, constant, 0. And you don't have kinetic, you don't have energy potential in this case. So you have the closed system, right? So it means that you only have U T2 minus U T1 equal to the Q plus W. But this case like Q plus W, W itself is equal to B0 because it's constant. So you only have the U and Q. So the Q itself we can divide N multiple by C plus delta T. That's we can have the definition of the CV. So CV in here, we can write the CV as function of the T and V. So we can take the limit delta V approach to B0. Delta T. So when you take the limit, you can use the partial differential of the U divided partial differential of the T at constant V. So you can write del U underline T V divided by dt. So this is at constant V. So we can write like this. So the measurement is made at the constant P. How about the constant P? And volume was changed during the heating process and definition Cp. Same way, same issue. So we can write Q equal to the U T2. Remember U plus PV equal to the enthalpy. So we can write T2 minus H T1 This is become NCP delta T. So here we can expand NCP T, T2 minus T, T1, right? So then, for the CP itself, you can use the CP at Tp equal to the dH divided by dt. This is at constant pressure. You can rewrite delta H underline at Tp divided by del T. So here it's constant pressure. So you can distinguish these two. One is for the CV, it's function of the internal energy, du divided dt. But for the CP is dH divided by dt. So this is definition of the thermodynamics with the temperature dependence U and H. This is need to memorize because somehow we need to prove later in chapter 6, like what's the relation CP and then CV, but it's respect to the constant pressures and then the constant volume, like how you going to expand or how you going to define these equations with relation with the CP and CV. That's why for the CV, we can have the du divided dt, and then for the CP is dH divided by dt. Okay, so we go to the ideal gas, but it's for the heat capacity like CP asterisk and CV asterisk. So the asterisk in the thermodynamics, it represents about ideal gas. So don't confuse. We have the H and U of the ideal gas. So the ideal gas is basically similar, but this is special case. So for example, like in the ideal gas condition, when we calculate the thermodynamics properties, we always go to the CP asterisk, and CV asterisk is for the reference. For example, we have the example of the some system, and we have the CP asterisk and then the CV asterisk. So we need to calculate the CP and CV for the some real system with respect to the ideal gas. So the CP asterisk and CV asterisk is also depend on the temperature only. Then, for example, why we don't have in the CP asterisk, we don't depend on the pressure, because in the ideal gas, PV is equal to the RT, like we discussed before. So it means like the H and U, it's depend on the temperature. That's why when you calculate, perhaps in the senior high school or in the bachelor, they have the function, the CP and CV, but they give you like it's function of T. It means that it's only the function of the temperature. We don't have the pressure. That's why it's a need to have the some coefficient or constanta to calculate. For example, if you just recall, for the CP asterisk, here I wrote CP asterisk. This is only function of the T. So we have dH divided by dt. So then for the CV asterisk, we have du divided by dt. This is what we expand before. Then if you supposed to be, you want to calculate like CP asterisk. If you still remember, you need to have the sum constanta Bt plus Ct power of 2 plus dt cubic, plus so on. So this is like what we used before in senior high school, like, oh, we have the coefficients and then depend on the temperature and then calculate. So because ideal gas PV equal to the RT. So that's the reason why it's only function of the temperature. Then since you have the H equal to the U plus PV, and for ideal gas PV equal to the RT, so we have H plus RT. So you can replace that the PV is equal to the RT, become U plus RT in here, right? So then we can write the Cp, replace the H here, become U plus RT. So it's become Cv asterisk T plus R. So why in here become Cv asterisk? Because remember Cv asterisk T is equal to du divided dt. Du divided dt is equal to Cv asterisk. And plus RT dRT divided dt. Because it's differential, dt divided dt is equal to 1. So you only have the R. So that's why Cp asterisk equal to the Cv asterisk plus R. Or you also can divide Cv asterisk T, it's equal to the Cp asterisk T minus R. So Cp asterisk, you can rewrite this all coefficients constanta. It's become A minus R plus Bt plus Ct power of 2 plus dt power of 3 plus so on. So the constant of A, B, and C, you can see in Appendix A2. In the behind of our textbook, there is a lot of appendix, so you can divide according to the constanta. And solve the energy balance equations. If you supposed to have energy balance, you need to know the change of the U and H. This is delta. So delta U and delta H only. So in here we can calculate the H with the reference states. So for example, like if we have the enthalpy, I can relate one of the some equations. Let's say here we have the HIG, yeah? Or you can that if you want to solve some of the reference states for the ideal gas. Let's say here I have the delta H. So the delta H itself we can solve by the HIG. For example, at the T, it's coming Cp asterisk, yeah, because H is Cp asterisk dH divided dt. So here T minus Tr. Tr, it means that the ambient, when you measure the enthalpy, like you would like to calculate the enthalpy, and then in these measurements, like what's your reference temperature? So this is, we call it the reference stage. So for example, like ambient temperature, you have the 25 degrees C. So at this times, I would like to measure 100 degrees C. So 100 degrees C minus 25 degrees C. So this 25 degrees C is the reference state. So that's what we calculate. Then we can try to divide UH for the ideal gas. So this is interesting to measure the calculation for the H and then for the U. For example, here we have a lot of definition for the H and U underline ideal gas at T. I just write in here for the IG, it means ideal gas. So I can represent here as IG. IG, it means ideal gas. So you can calculate the HIG. So here at T2 equal to the HIG at T1 plus integral, because ideal gas, so the Cp is only function of the T. That's why here we have T1, T2. Cp, don't forget, ideal gas is need to write the asterisk T dt. That's why thermodynamics is symbol is important. So you cannot miss writing. If you just write H, I don't know that this is ideal gas or not. So it's better like to write HIG so that it's more clear. So here we can write the HIG for the T, it's equal to the HIG TR. Yeah, here is temperature reference or temperature state. So because the ideal gas, the reference temperature state is equal to B0, so you can use the HIG T is equal only with the integral Cp asterisk T dt. So here you can write Hij, right? T, it's equal to the integral Tr to T for the Cp asterisk T dt. Then why in the ideal gas for the reference states it's equal to B0? Yeah, we choose it's equal to B0 because Tr is absolutely 0 for the ideal gas. So we don't need to consider about the Tr in the ideal gas. Then for the U the same. U in here the internal energy. Here I put underline and Ig. So here because U is equal to the H equal to the U plus PV, right? So remember before we discuss about the thermodynamic identity. So if you would like to calculate the U, it means H minus PV. So here because of the ideal gas, so the PV is equal to the RT. So H minus RT. So that's why this is the reason why in here like we write H minus RTR plus integral Cv asterisk Tr to T Cv asterisk T dt. So then we can simplify here because the Tr is equal to B0. So it means that you don't have this. You don't have any cons with the Tr. So it's only have the this ones you don't have, yeah. So it's only have Cv asterisk. In the end, you only have integral Tr to T. It's Cv asterisk T dt minus R Tr. Okay, so then we go to the assume that the Cp asterisk and Cv asterisk, they are temperature independent. So we can write for the Hij at function of the T because this is temperature for the temperature independent, you can just write Cp asterisk T minus Tr. And the other for the Uig, the same. We can write Cv asterisk. So you have Cv asterisk T minus for the Cp asterisk Tr. So then we can start to divide the other. If you take the Tr is equal to B0, so we can have the Hij at T, it's equal to the Cp asterisk T. And then for the U, the same. Uig, I just write here. It's equal to the Cv asterisk T. Okay, so I think in this case, like this is how we define the a proof, yeah, between the H and then for the U, the same way, like it's not difficult, I think, compared than the not really many mathematics derivations, yeah, for the thermodynamics parts. Then we can start for the curve, I think, like how we use this all application into to the real. So in the real, we will later like see that how the relation of the H and U, we don't need to use the analytical calculation like this, but we can use the curve or the figure like how to read the enthalpy and entropy into to the applications. For example here, the thermodynamic properties of the real fluids. Before we discuss only for the ideal gas, but currently it's for the real fluids. So for the real fluids, like they have the interaction, like thermodynamics properties, of course, it cannot only depend on the temperature. Like we discuss ideal gas, PV equal to the RT. It's only function of the temperature. But for the real, suppose you have the compound, it's one component, and then you have the phase. The phase, let's say it's equal to 1. So in this case, you have degree of freedom, it's 2. So you can define your system in the measurements. It's the function of the temperature pressure or the temperature volume or the pressure volume. So it's mostly like depend on the which constraint that we're going to depend on. So they are of course more complicated than those of the ideal gas. That's why we need the experimental data like the steam table. I believe that you always use the steam tables even in unit operations calculation or unit operations courses, yeah. And then we also can use the steam tables or appendix A3. This is from the table. And for the figures, also we have the Euler diagram. We can use for the steam. We have also for methane, nitrogen, hydrofluorocarbon 134, one kind of the refrigerant. It's depend on the which kind of the compound that we use. And we have also enthalpy entropy chart like Euler diagram. So this is interesting in the useful of the turbine and then the compressors. So please remember, because it's after you graduate, you will somehow use some applications in the if you are process engineer or field engineer, you will come back to the theoretical to see that this is possible or not, and how about the quality of your compound. For example, like if we have the enthalpy and entropy from the Euler diagram, so you can use like this figure is for the steam. So you can check your steam quality. Is it how many percent wet? For example, for turbine, it's not good if you have the liquid phase. So we need to have the higher than 98% of higher than 90% is the best, or even 100% for the steam quality. Because if you have the small liquid, they will erode your turbines or the blade of the turbine. They will corrosions. They will have the erosions in the blade. So it's not good for the turbine, even for the compressors. And then the same for the HP, for the enthalpy and the pressure charts. This is mostly used for the refrigeration problems. Like refrigeration, we use every day in daily life. Like if you have the refrigerator in home, right? So refrigerator, here is use the refrigerant in the cooling system. The same like the AC, air conditioner. This is also we have the refrigerant. We use the refrigerant to cooling our room. So the same for the application for the refrigerant, to see that the efficiency of your refrigerant, to see that your refrigerant, how much the efficiency of this compound, is it good or not, and which condition it's you can reduce the or optimize the condition, reduce the cost, and then you have the optimized condition. This is mostly is used the HP. And how about TS? TS chart is useful for the engine and then the cycle analysis. So we all use the experimental data to predict your properties. One example, this is normally a steam table. I believe that all of you know this water and then the steam, yeah. This is mostly we use. If you see that how much the degree of freedom, let's say that for the saturated steam, this is the properties for the saturated, yeah. So you can see saturated steam. When you say that saturated steam, they consist of two phases, vapor and liquid. So it means that you can use that degree of freedom to check your constraint. I have the 2, and then the compound of course is water. So you have 2 minus 1 minus 2 for the phase, because saturated it consists of the vapor and liquid phase. So it means that your degree freedom is only 1. Can you see in here? It's supposed to be, I have the temperature, it's equal to the 30 degree, yeah, 30 degree, but my pressure it's around 4.246. So you only need to use one of them, and then you can know the properties like specific volume, internal energy, enthalpy or entropy. So you don't need to use to constraint like T and P because you have the one constraints, or you can choose the temperature or you can choose the pressure, and you will get all of the data. It's different with the superheated systems. So superheated is special. For the superheated system, the next one, you have the phase is only one. Yeah, superheated, it means that the phase is above the saturated condition. So it means that your phase is only one. Then you can calculate by the F equal to the C minus P plus 2. So in this case, you have the compound, it's 1 because water. And then minus the phase itself, it's superheated vapor, it's 1. And then equal to the 2. That's why in the superheated vapor, you see that you have the pressure function, fixed pressure function, but different temperature, right? So you need to define your condition. You need to know the temperature and the pressure when or which condition that you would like to measure, and you will get the specific volume and then internal energy, enthalpy and entropy. So you can define from this appendix A3. Yeah, so in the textbook we have this appendix. And how about this diagram? This is interesting. This is enthalpy, entropy for the Euler diagram. So if you see that, pardon me if the curve cannot be enlarged, but I can tell you like specifically how we read this curve. So you see that this is the dash yellow line. This is yellow line. It means that the saturation line. So if you check like in the phase equilibria, I can say that this is, for example, we have the phase equilibria, yeah. Okay, so I have the let's say like some specific the temperature. Let's say that I define or measure this phase equilibria at 25 degrees C. So I have T, I define it's equal to 298.15 K. So I have the curve, it's like, if you see that, it's like a half circle. Yeah, of course, it's not totally like half circle, but it looks like the half circle. So here I have the X, I have the Y. This is mostly in binary compound. It's for two system. And then here you have the pressures. So you see that here, we define that each of the binary system, they have the highest point. This is, we call it critical point, or C dot P, critical points. So the critical points, it means that you cannot define the phase, which is, this is the vapor is a vapor or it's liquid phase. You cannot distinguish between each. We cannot differentiate like this is bubble point, or you have the dew point, or this is the vapor phase or liquid phase. So when the critical point it's happen, like when you decrease the condition or the pressure, you will see like it's actually like half by half. So like 0.5 for the vapor phase and then the other 0.5 for the liquid phase. So you can see it's from this curve, I can tell that I just write the red line. So below the critical point, this is, we call it bubble line. So bubble line, it means that it's like boiling water. You have the liquid water, you put the heat, and then you will see the bubble. So small bubble, yeah, this is, we call it bubble. And then the other curve, the other line, this one, this is, we call it dew line. Come back to the phase transition, yeah, bubble, it means like liquid phase into to the vapor phase. So dew line, it means that vapor phase into to the liquid phase. So they will transform into to the bubble and then dew line. So if you see that the critical point, yeah, li jie tian, yeah, or you can, or bubble point, you say pao tian in Chinese, yeah, or bubble line, bubble points. And you have also dew points, lu tian, yeah. So in here, like you have the dew point. So when you have the everything phase inside, like under this curve, this is, we have the vapor and liquid phase. So they have two phase inside this under. But above the critical point, this is, we call it supercritical, or you can say that superheated above this line, outside this line, outside the saturation line, they only have consist of the one phase. So either this is vapor. The same with this curve. If you check this curve, yeah, inside this curve you have the quality. So let me find the definition here. Here, this is the moisture, yeah, moisture of your steam. And on the other line, this is the pressures. So you can see like the pressure and the quality of the steams together, because in the bottom, like in the inside of the line, they consist of two phase. So of course, like your steam quality is not 100% is the superheated vapor, but they have perhaps 10%, 20%, 30%, and so on. So approach to the left side, it was the, we can see that the pressure, yeah, the pressure is around 5,000. This is, we call it saturation line or subcool. And here it was the superheated line, or for the vapor phase. So we have here like a saturated vapor and saturated liquid. So you have in here also, we can see like, suppose you have entropy is isentropic condition, because here it was the, if you see that the line is looks like diagonal, this one is the pressure and the temperature in the right side. So this is all is temperature. Yeah, this temperature. So you can read, for example, like I have the each condition, one condition 10 megapascal, perhaps in here, yeah. I just give one example, and then I have the temperature around 500. And my process is in the isentropic condition. I reduce the pressure until at the specific point. So perhaps I reduce from 10,000 kilopascal to 100 kilopascal. And how much entropy or how much the enthalpy? So I can see that the change of the states between the state 1 to the state 2. So this is, I can calculate definitely delta H. And even I can check the quality of the steam. Or otherwise, I have the isothermal condition or the temperature the same from the state 1, and then, but the pressure is different. For example, the pressure is 40,000 kilopascal to 300 kilopascal or 250 kilopascal. And isothermal conditions, and how much the entropy. So we can read in the bottom is for the S or delta S, change state of the S. Or I can check like from the superheated, like the third lines, yeah, the superheated conditions here. And then I have the some specific condition, I reduce the pressure until to 30 kilopascal. How about the quality of my steam? Is it two phase or one phase? So we can see everything in the Euler diagram. So it's more easy and more convenient compared to those of the steam table. Steam table, of course, you only can, it's convenient to read, but it's not give you a lot of information because you don't know the steam quality. Of course, like saturated, it's two phase, but we cannot see like calculate the quality of the stream. We need, of course, the curve. So we can calculate the quality of our stream, our steam. Okay, so then we go to the next for the how to read easily. So here saturation line or the moisture line. So here it means dry fraction line. Still remember, like I discussed before, that in the curve you will see like it's two phase, it's not only one phase under the curve. That's why here we call it dry fraction lines, and you can read enthalpy and entropy in the curve. Then the same, the blue line here, this is the temperature lines, indicates that you have different, the green line, it's the temperature lines, and then this is indicates that you have different temperature, and the pressure is the blue one. So the same dry fraction lines, and then which the enthalpy and the entropy. So you can divide with different pressure and then with different temperature lines. Then we can also practice one example, yeah. This is how to read the molar diagram. If I have the pressure 1, it's 5 bar. So 5 bar, remember the unit, it was in the kilopascal. So you need to convert into the kilopascal, and then you can calculate the curve, calculate for the delta H, yeah. So in here we have the delta H, or you can use the delta H. It's much more easy. So the state 1, remember you can write the delta H for the heat drop, yeah. State 1. So you can have the state 2. So in this one you have, you know the P1, you know the T1. T1 is 200, and then in here is 5 bar. And the P2, because we want to know the heat drop of the condition, you have the 5 bar, and then here is 0.2 bar. Like how you calculate the heat drop. So we can read from the curve, from the molar diagram. This is for practice. For example, like I have 200 degrees here. The green line, it represents of the temperature, and then for 5 bar. So here is the pressure. So this is initial state. And then for the second, I want to go to the 0.2 for the second state. So how it goes? So we can move the curve into to the 0.2. Of course, it should be in isentropic condition. So this process, we should assume that isentropic. I don't discuss yet about the isentropic, because isentropic we're going to discuss in chapter 4. So in the chapter 4, when you have the isentropic conditions, it means that you have the Q, it's Q divided by T. You have the S1 and sigma MKS1. For example, sigma MKSK. So this is plus Q divided by T plus S generation. So we can assume like when they are isentropic condition, of course it should be steady state. This is the first. And the second, no heat loss. So the Q, it should be equal to be 0. And your S generation, it should be reversible. Reversible, it means you don't have S generation, it's equal to be 0. So basically, I can write for a little bit to introduce to you, yeah. So this is sigma MKSK, depend on the unit, of course, plus Q divided by T plus S generation. So this is what we're going to discuss in chapter 4. So when they are steady state, this is you don't have the ds divided by dt is of course equal to be 0. No heat loss, the Q is equal to be 0. And then you don't have S generation because it's reversible process. So when you have the irreversible process, this is cannot be equal to be 0. This is S generation. For example, a reversible process. If you have the chemical reaction, A go to the B, and then B can come back to the A. This is reversible. But if you go to the A to the B and they cannot come back to the A state, this is, we call it irreversible. So that's why S generation, when you say that is isentropic condition, so this is, should be at this condition, or S1 equal to the S2. So this is, we call it isentropic. Okay, here, come back to here, like 5 bar to 0.2. So you can see in here even the enthalpy for H2. In the other side, you can read also for the H1. Okay, so you can see even from the curve that when the 0.2, your steam is not even like one phase again, but it's in the two phase because they are inside of the saturation line. So they have the vapor and then the liquid phase. So underline or under curve, this is have a two phase. Okay, so we have the H1, we have the H2, like we discussed before. And we can calculate the H1, for example, like H2, you have the H1 2500, and then for the H2 is 1800. So 2500 minus 1800. So you only have remain for the heat drop, it's equal to 700 joule per mole. So this is one example easily. If you use the Euler diagram, it will going to help you because you can read enthalpy, entropy, the quality of the steam, even the molar volume, the specific volume, and then you also can see that at this curve, like it's good for your operating, for your equipment or not. So it's more easily to see. And then the other is TS diagram. So you have the temperature, you have the entropy. The same on the yellow line, in this case, this is under curve. This is actual equal to the saturation line. So everything inside this curve, it's have two phase, the same. So we can see that from this curve, we have the TS. Let me find the bigger version. So we have the constant superheat here. Yeah, so here is constant superheat. And then you have here is constant quality. So everything is in the persons. And the other is constant enthalpy. To the other side, this is constant enthalpy, constant quality. And we have the other, this one is temperature, and then you have the entropy in this case. The same way, the highest point here, if you check or you divine, this is the critical point, like we discussed before, yeah? Critical point. And here it was below critical point, this is saturated liquid. Above the critical point, after the critical point, this is saturated vapor. And all of this is superheated steam. So if you supposed to be would like to read one example, like we have here some specific temperature. Yeah, this one is temperature and this is the pressure. This is the, let me find the volume here. And this is the enthalpy, the constant enthalpy. So if you supposed to be, you would like to see some constant enthalpy or isenthalpic condition, they will go to this red line. And then you will read like how much the temperature that you have. So for example, here I have 214 degrees C. Yeah, it's from 500 and then I have the condition, for example, like I have the original temperature 500. And then isenthalpic conditions until at the some pressure and then how much the temperature. So you like Joule-Thomson case. So you can see like one time from this curve, or you can also use the appendix to calculate the H1 at the T1 P1. You know the H2, but only the pressure. And you can read for the temperature in this case. Okay, so I will go to the refrigerant, I thought. So before we read the refrigerant, it's better to know about the specific of the equipment about refrigerant. So refrigerant mostly we use in the case how to calculate the refrigerant quality. Yeah? So we mostly use in the daily our life, like we discussed before, refrigerator. We use also for the lengchi, for the AC, and everything's in the equipment like the refrigerator or the even the equipment for the company for the cooling systems, they use the refrigerant. So the refrigerant principle that you should know even for the AC. Maybe we use the air conditioner, but maybe some of you didn't know like how the air conditioner can be cooling down the temperature inside the room, because like the heat or the temperature inside the room, they will suction go to the cooling system, and the cooling process is done by the refrigerant, and this will go outside. That's why, like, when you touch the refrigerator in the behind of the refrigerator or behind of the air conditioner, you will feel hot. Yeah, the system. How the system itself. So they will go to the low vapor pressure and then they go to the compressor. In this case, they want to compress the pressure from the low into to the high pressure, and they will go to the condenser. So condenser, in this case, they will go to the high pressure liquid and expand into to the low pressure and go to the evaporator. So the cooling itself, like, because the refrigerant, they absorb the heat, yeah, from the air. They absorb the heat from the air, and then that's why the air, they will cooling down, and then they will remove this heat into to the behind or after the in the by the condenser. Yeah, so in the condenser here, like, it's mostly like the temperature is high because like they absorb the heat, so the temperature out it's hot. You can try in home. You feel like in the behind of your refrigerator, you feel like hot. There is some air, you feel like it's hot. It's coming from the refrigerant absorb the heat. Yeah, so they will absorb the heat in the inside the refrigerator. That's why they will exchange this process. That's we call it also heat exchanger. Heat exchange. So they exchange the heat from the hot into to the cold. So first, the function of the compressor. So this sketch will never change because inside your refrigeration or inside of your air conditioner, it consists of this equipment, compressor. This is the first step in the refrigeration cycle that you cannot neglectable. And then this compressor, they will increase the pressure and then become the compressor. So the compressor is one piece of the equipment that they increase the pressure. This is the function of the compressor. The name is compress. So like you from the low pressure, they will increase into to the high pressures. So then lift the compressor into to the high pressure, and of course, the pressure, they are linear relationship with the temperature. When you increase the pressure, you increase also the temperature automatically. Then, after they go to the compressor, they will go to the condenser. So the condenser is practically like this. So the condenser or condenser coil, it's one of the two types of heat exchanger that used in the basic refrigeration loop. So this compound is supplied with the high temperature and high pressures, because after the compressor is high pressures, of course here it should be like high temperature and high pressure specification. And this vaporize the refrigeration, it's coming off to the compressors, and the condenser remove the heat, right? Remove the heat from the hot refrigeration or hot refrigerant vapor gas, and until it condense into to the saturated liquid state, or you can say that condensation process. That's why after they absorb the heat, the vapor phase, the compressor, because it's high pressure and high temperature, they become a vapor phase and they will condense into to the liquid phase. So after they condense to the liquid phase, they will go to the expansion device. So this is expansion device. Actually, it's a Joule-Thomson or isenthalpic condition, because they expand from the high pressure and then go to the low pressure. This is pressure drop will cause some that refrigerant is quickly boil. So they create the two-phase mixtures. Normally in expansion valve, they will create into valve two-phase mixtures. Then from the boil, we have the evaporator. So evaporator here, we have the two-phase into to the one-phase. So the evaporator is the second heat exchanger after the condenser, and they are standard refrigerations we use in the refrigeration cycle, yeah, to absorb the heat. So this happen when the refrigeration is entered to the evaporator as the low temperature liquid at low pressures, and then the fan force the air across to the evaporator's fin and cooling the air by absorbing the heat from the space in the questions into to the refrigerant. So this is function of the evaporator. But if you see that in refrigerator or in the air conditioner, of course, like this equipment is not big. It's they try to decrease the size as much as they can. That's why right now we can see like it's more convenient to move. Yeah, long time ago when this device it's found, it's the design is even the compressor on the expansion valve, it's quite large, and at that time it's impossible even to move the equipment. It's not convenient for the design, engineering design. And then they start to use the small evaporator and the small compressor, and to easily then currently like you can use the evaporator, even you can use the refrigerator, even the air conditioner freely move, and it's more convenient for the design. And this is one of the refrigeration cycle. So if you see that here, this is consists of that device. So please remember, this one is the cycle of for the evaporator. Okay, on the top it's condenser, and this one is compressor. And the other line is the Joule-Thomson or expansion valve. Yeah. So if you see that evaporator is normally like 10 degree, for example, I have the condition like 10 degree, minus 10 degrees C. It was the evaporator temperature. It's normally it's low pressure, 0.2 megapascal. It's around 2 bar. Then I compress the pressure into to the 1 megapascal or 10 bar. So then in here we define this is the initial one, they go to the second one. And then the condenser have the temperature 40 degree. Of course, like they give you the condition like the temperature. Yeah. So here, for example, the condenser, it's 40 degrees C. So we got to increase the pressures up to 40. If you supposed to be, you have 50, then you got to increase the pressure up to 50 degrees C. Then they will condense into the saturated liquid phase and expands into 0.2. So in this case, like this is, we call it one cycle of for the refrigerants. So you can read enthalpy, you can read the pressure, and you can calculate the efficiency of the refrigeration. It's from like how much the evaporator heat you use, and then the compressor, the work from your work of the compressors, then multiple by 100%. This is, we call it coefficients of performance of the refrigerants. So you can calculate the COP from the refrigeration cycle. Then this is one example, like we have the subcooled liquid. This is saturated liquid. On the bottom we have liquid and the gas mixtures. On the other side, we have the superheated gas. This is a saturated vapor, and of course, we have the critical points. Like if you would like to calculate to see the curve, so we have here like this is constant T. So you will know that this is constant T, constant temperature. This is how we read the temperature. 50, the same, passing through to this. Minus 10 degrees C, same. This is constant temperature lines in the degrees Celsius. And then the other side, this is pressure lines. Yeah, the green one. 1 megapascal, 0.2 megapascal. So please don't forget about the unit. In here, the pressure in megapascal. The other is an enthalpy, kilojoule per kilogram. Then we have the other, it was the entropy line. So entropy line, it's like diagonal line. So this is entropy line. So we can see like this is entropy line. It's isentropic, or they are have the difference entropy or in isentropic condition. So if you come back to this curve, that's why like we read at this line, yeah, because it's mostly compressor is done at the isentropic condition. So they are isentropic conditions. So in this case, we have the isentropic line or entropy lines. So the unit mostly in the mass because kilojoule per kilogram in the mass unit. Then enthalpy. Enthalpy, we can see the violet one. It's like from the top go to the in the bottom. This is enthalpy line. Isenthalpic condition, the same in kilojoule divided by kilogram. Then we have the other is vapor volume. Vapor volume is mostly like the yellow line in the horizontal, almost horizontal. Yeah, this is in meter cubic per kilograms also. For the refrigerant, for example, we have ambient temperature 25 degrees C, room temperature 0 degrees C, temperature entering for the compressor 1 degree C, living compressor 58 degrees C, and entering expansion valve it's 38 degrees C. So actually you can guess and make a sketch like before, yeah. So you have the compressor. So in here for the compressor, and then you have here condenser, right? And then here you have the expansion valve. And then the other side you have the evaporator. So you can read actually like this one cycle. Evaporator, this is condenser. So for example, like ambient temperature 25 degrees C. So you have the temperature entering compressor. So the temperature entering compression is 1 degree C. And then temperature leaving compressor is become 58 degrees C. So you can entering and then condense. Yeah, condense it means go out from here is 38 degrees C. So in the evaporator, of course, is also the same 1 degree C. Yeah. So in here, because the evaporator 38 degrees C, this is in inlet, the same expansion valve. Yeah. So they will drop. This is entering. They will drop the pressure here. So here 38 degrees C. Then how are we going to solve this problem? So we can start to make the compressor, evaporator, condenser. Like before, we have the 1 degree C, and then in here you have the evaporator, and then the compressor compressed to the until the 58. Oh, but here like is different refrigerant. Yeah, in this case, R134 in here also the same. So we have the entering compressor 1 degree C, temperature leaving compressor 58 degrees C. It seems like this is have some efficiency, like how we read the curve. Yeah, for example, you have the evaporator. Let's say here it's because we have they don't give the exactly like conditions or unit here is not, oh, this is T is equal degree C, but the pressure is in the bar. So for this case, I think they don't give you the pressure. They need to give like the pressure condition, not only the temperature in here. So we can also like read based on the temperature leaving like the expansion valve 38 and then entering compressor. For example, like the compressor here, we have the minus 10 degrees C. Yeah? So in here, minus 10 degrees C. So this is the evaporator, and then until which temperature? In here, like we see that 40 degrees C. So 40 degrees C, and then you will have the condenser, and they will expand into the come back to the evaporator. So they will expand the temperature, and then until the H4 and then H3, they are isenthalpic condition. Expand, it should be in isenthalpic condition. It seems like the condition a bit different with the previous one, but don't worry, like you can read also, like for example, like temperature entering the compressor, it's 1 degree C. So it's meant like you need to entering you can adjust that it should be like at 1 degree C, it's entering the compressor, and then leaving to the 58, yeah, in the 58 degree C for the compressor leave. So it means that when compressor leave, they are actually like is entering for the condenser, and then it's reduced into 1 degree C, yeah, for the expansion valve. So then this is one example how we read the refrigeration R134A. And then the same, like here I define evaporator, condenser, compressors, and also the throttling valve. So throttling valve or the expansion of the valve, they are actually like similar case, the same. So here you have the H1. This is the H1. You can read the H1, 391.18. For the 2, it's the same. We can read need to follow the line, the temperature lines, yeah. Don't put the straights, but it's a little bit curvy. So you need to follow the line because the T and P is different. So H2 is equal to 444.1, and the condenser also the same, and the throttling valve, yeah. So here we have the H3 equal to the H4 equal to 252 because they are isenthalpic conditions. And the same way, like if you have supposed to be like some such of the condition, for example, like I have the key, like if I have the refrigeration, but I have the subcooling or the super, like subcooling. Subcooling, it means like degree heat, yeah. Maybe, for example, like I have the refrigeration, for example, like some condition. I give you perhaps one example of the questions. It's much more easy. Let me find the question. For example, like I have okay, this is the most easily. Like HFC 134A, like hydrofluorocarbon. So it's used in the ideal vapor refrigeration cycle. First, they operating the cycle at minus 30 degrees C. And then in the evaporator, in the minus 30 degrees C, and 40 degrees C at the condenser. So 40 degrees C and then minus 30 degrees C. Then in the operation cycle, the degree of superheat and degree of subcooling is added to be 10 degree. So it means that I add and I remove 10 degrees C. So the refrigeration released by the isenthalpic conditions, this is isenthalpic condition, and then you can calculate the rate of refrigeration, coefficient performance, and the rating of horsepower of the refrigeration. This is one example. So when they have the degree of subcooling, so it means you have the minus 30 degree of superheat, yeah. It means you plus 10 degrees C. If they are subcooling, it means 40 degrees C minus 10 degrees C. So they have the yellow line. It's in the 30 degrees C here. So that's why here, the first point when they are degree superheat, you need to draw the yellow line, and it's become your first point when they are intersect with your red line. Then increase compressor into the isentropic conditions, and then go to the left side, degree subcooling. So they are not exactly in the subcooling, but it's like a degree of subcooling. It's at 40 degree C minus 10 degrees C. It's become like 30 degrees C, and then release into to Joule-Thomson or isenthalpic throttling valve, yeah, throttling valve device. Okay, so how about if we calculate the properties of the two mixtures? The properties of the two mixtures, this is we can use the lever rule. Lever rule, like for example, if you want to check the quality of the steam, we can use the two-phase mixtures or lever rule. For example, you have theta in here equal to the omega 1, theta 1 with the cap plus theta 2. This is omega 2 and then theta 2, yeah. So in here, like it's based on the mass. So in here W, here W1, W2, or omega 1, omega 2, this is actually is mass fractions. So you have here, you can rewrite W1 I Ti plus 1 minus Wi. This is equal to this one. It's equal to W2. Because why? W1 plus W2, it's equal to 1. Then multiple by theta 2. So W1 and theta 1 are the mass fraction of the system and the value of variable in phase 1. So this is general equation that you can calculate enthalpy, you can calculate entropy, you can calculate the any kinds of the thermodynamics properties, yeah, from the general equations. And for the mixtures, for example, you have the steam and water. So the mass fraction of the steam is steam quality is defined for the steam quality is frequently expressed in the percents. For example, like we discussed before for the Molar diagram. Molar diagram, it's calculate the quality of the steam. So in this case, we can see that the fractions of the quality of the steam and water, they are mostly like based on the percents of the two-phase mixture. So in here, we have the two-phase mixtures will fall along the line connecting the properties of the individual phases. So the lever rule in the equation 339, we can calculate for the enthalpy. For example, we have enthalpy delta H in here with the steam quality 10% and the other of course 90%. So we can calculate the total enthalpy. Or the other is property changes at different phase. For example, I want to calculate the molar enthalpy of vaporization. So we can calculate delta vaporization enthalpy. It's equal to the molar enthalpy of the V, vapor phase, minus molar enthalpy at the liquid phase. Or fusion or melting, yeah. We can use the delta H fusions and equal to the molar enthalpy at the liquid phase minus molar enthalpy at solid phase. This is fusion or melting process. Or the other is sublimation. Sublimation, it means that the vapor phase, solid phase change to the vapor phase, or vapor phase they change to the solid phase. In this case, sublimation. For example, if you know that the chloroform, not chloroform, so we have the capstar. Yeah, capstar is kind of the chemical that you put in the room if you supposed to be would like to have a good smell. So we use the capstar. So here is a solid phase, and then they will decrease in. They will like evaporate into the vapor phase. And the sublimation is like dew point, like the air, the dew point, they will condense, yeah. This is condensation, sorry. For the sublimation is from the vapor phase into the solid phase. So you have the HV minus the HS. Then we go to the thermodynamic properties of solids and then the liquids. We have this the PV, yeah, supposed to be like in the ideal case we have the PV equal to the RT, but in the solids and the liquids case we have the very small of the PV. So this is we don't need to include the PV in this case because it's for the liquid phase we only have a very small amount of this. So we only have that the in this case that the for this case like for the U H for the enthalpy it's equal to the U underline. So this is for the liquid and the solid phase. So for the incompressible fluids like the solids and most liquids are far away from the critical points, like, and then we have the dV divided by dP is function of the T, yeah, because remember that the volume is the only function of the temperature in this case. So and the U, Cp, Cv are function of the temperature only. And we have actually some correlation for the solid. So long time ago, the Dulong and Petit correlations, they mentioned about the Cp for the solid, and then they divide like one equation. This is we have the 3nR 24.942 and joule per mole K. So N it means the number of atom in the formula unit. So if you have the some solids like the PbAuAl, so this is at 25 degrees C, so 26.8, 25.2, and 24.4 joule per mole Kelvin respectively. This is from the experimental result. And we try to predict use these equations, and then the result is practically like, for example, like the Fe3C, yeah. So in here we have the sum of the compound is have the 99.8 joule per mole K. This is use the equations, and the experimental value is 105.9 joule per mole K. So I think like this is practically close, yeah.